All right, today, lesson 6A, our topic is natural logarithms. We've just left common logarithms, base 10. The natural logarithm, we'll just go ahead and fill in the blank here of our notes. Natural logarithms are base E logarithms. There is a number called the number E. It is a lot like pi in the fact that it is irrational, non-terminating. The actual decimal for the number E is 2.71828, and then it just keeps on going, never stops. But if we want to just use our own, like pi, we typically say 3.14. E, we typically say is 2.7. Some people actually celebrate E Day on February the 7th. I don't even know if we were here. Were we here on the 7th? So anyway, the reason why we call it E, and there's some discussion on this, most people think that it was because of a man named Euler, and it doesn't look like Euler, but it's pronounced Euler. Mr. Euler actually discovered this, and if we had time, we would take the time to do a little experiment to see how he came up with it. It's really cool. He discovered this by working with that compound interest formula that we learned a few days ago. Just being curious, like good mathematicians do, he worked with this formula and he discovered our famous number E. And we use E to represent interest that compounds continuously, anything that grows in what we call a continuous way. Or maybe it's something that decays continuously. Continuous growth or decay is always modeled by the number E. And I'm sure you'll see that in future math classes and science classes. Okay, so let's get into specifics of your homework. 18 to 25 will be exercises in changing exponential form to log form and log to exponential. But you notice that the base of the exponent is the number E. And when E is the base, we don't have a logarithm, a common logarithm, we have a natural logarithm. So why don't we just take a second and familiarize ourselves with a couple of buttons on your calculator that you're going to use a lot. One of them is the LN button, and that's what we use for natural log. And then another one is e to the x power. And they're pretty close together on your calculator. So just locate where they are. We're not going to use them yet, but you will use them quite a bit to finish your lesson tonight. Well, the same way we took exponential form and changed it to log form with common logs, it's basically the same process with natural logs. So let's look at letter A. Since E is the base, this is typically the most commonly made mistake people make. They don't remember that when E is the base, it has to be a natural log. So if you were to put log here, that would be incorrect. Natural log 30, logarithms always equal exponents. And that's really all you have to do. You do not have to grab your calculator and find the decimal equivalent of natural log 30. All you have to do, according to the instructions, is take an exponential equation and make it log. Natural log in this case. Okay, letter B is a natural log equation, so we're going to turn it around and make it exponential. So when you see natural log, you know that it's got to be E raised to some power. And the natural log here tells us that the power is 42. Logarithms always equal exponents. So this would look like e to the 42nd power equals x. All right, letter C, another e to the power exponential equation. So in natural log form, it would be natural log x. Logarithms always equal exponents. So natural log x equals 3. Here's a natural log equation, so we need to write it in exponential form, but we got to use e as the base. E to the power of x is equal to 18. And that's a pretty good representation of what you're going to do on those problems 18 to 25. Change from log to exponential, vice versa. Remembering that natural logs mean base E. All right, do you have any questions so far? Okay, the good news about the properties. Remember those properties, quotient, product, power? We had that killer homework assignment a couple nights ago that everybody hated. We drilled those properties. Well, the good news is those same properties that work with common logs, they also work with natural logs. So this is just a review basically of those properties. We need to use the properties in order to take multiple logarithms and turn them into a single log. Okay, so I'm going to write a line underneath this problem letter A, and I want to see if it makes sense to you. And I'd like for somebody to maybe tell me what property I used to get from blue to red. Hunter. I used the power property. Good call. Power property says these numbers that are factors can become exponents. 2 cubed is 8. 4 squared is 16. Okay, now somebody give me the property that says two separate logarithms that are being added can be joined together using what, Maggie? That's the product property. So we're going to multiply 8 and 16 together. I think that's 128. So my final answer here for letter A, using basically two of the properties we learned, will be natural log 128. And you do not have to evaluate that. Don't give me the decimal form. You just finish by writing a single logarithm expression. Okay, so let's just jump right into letter B. Power property again. See if this makes sense to you. 3 to the 5th power. 243. Over here, power property, 9 to the 2nd, 81. Okay, so Sarah, give me the property I'm going to need to use now to make these two logs become 1. Okay, tell me what you do then. So you just described what operation? Okay, and the answer to a division problem starts with a Q. Yeah, this is the quotient property. So I do need to reduce this. So 81 does go into 343 3 times. So my answer here would be natural log 3, using the power and the quotient properties. Okay, so let's see, Heather, can you tell me, using the power property, how I would change this? Just using the power property, what would it become? Okay, natural log 216, that's 6 cubed, plus natural log 81. And let's see, Kate, what property will we need to use now? The product property, 2 logs being added, can be joined together as 1 log using multiplication. No. Here's the power property. Numbers that are multiplied can be made to become powers. Like 3 became the exponent for 2. The product property says 2 different logs that are being added can be put together using 1 log and multiplying. I'll just write it out. So can you tell me what that is? 216 times 81?
It's 17,496.
Okay, and that would be my answer for letter C, natural log 17,496. Any questions so far? Quick review of the properties. It's going to be really handy on your test Tuesday, along with a lot of other things. Okay, part 3 is let's solve some equations involving powers or bases of E, exponential equations that have a base of E, and then we'll also look at some natural log equations. So let me give you a big tip here to remember. Doesn't always apply, but you need to be on the lookout. You need to look into, your first objective needs to isolate e to the power. That needs to be goal number 1. Get e to whatever power. I just used x, but it could be x plus 5, it could be 2x, whatever the power is. You need to isolate e to the power first. So Devin, in this problem, what will need to be done first to isolate e to the power? Subtract 9. Good call. All right, so negative 3 times e to the x is equal to negative 5. And Casey, the next move to undo negative 3 being multiplied? Divide by negative 3. Good call. So I'm down now to e to the x equals 5/3. Okay, now we're in great shape. When we get e to the power isolated, then we're ready to change it over, just like we did before. We always change exponential equations into log form, and in this case it's going to be natural log form. Change to natural log form. Get e to the power by itself, and now I want you to write this as a natural log equation. Okay, so, hey. Sure. Yeah. Whitney, can you tell me what that would look like as a natural log equation? Good. Nice. Now your calculator is going to do the work. So hit your LN button, natural log, and it probably opens up a left parentheses. Put in 5/3, close your parentheses, and these are going to be rounded just like the previous assignment, 4 decimal places. So Whitney, go ahead and give us that number. 0.8. Okay, show of hands if you got it right. Okay, so the big trick here is getting it to e to the power form, then it becomes easy. If you know how to change exponential to log, your calculator is going to do the rest of the work. Any questions? All right, let's try another one of those. Once again, your focus is isolating e to the power. So give me a first move here, Hannah. Subtract 4. Okay, Devin, give me a next move. Divide by 3. Good. Okay, and I'm down to e to the power. E to the power is isolated. So Maggie, what would this look like now converted to a natural log equation? Nice. Now at this point, you really don't have to write anything else down. I would just let your calculator do the work here. Natural log, 2/3, and then just hit enter. And that's a decimal. You do not have to write that decimal down. Just let it sit there. And now to solve for x, what will we need to do? Just divide by negative 3. And that's going to get you to your answer. And we'll say approximately, since we're rounding, what is that, Hannah, what is that? Okay, if you got it, raise your hand. Okay, are you following the process? Get e by itself, change it to a natural log, turn it over to your calculator basically from that point. Okay, now let's look at some that are log equations. Well, with log equations, we need to think about removing any number. In this case, we have 5 being multiplied. We might have 5 being added or subtracted. It really doesn't matter. But if there's some operation that's happening in front of our log, we need to get rid of it. Okay, so you might think of clearing the space in front of log, whatever works for you. Here, I need to undo multiplying by 5. So on both sides, I'm going to divide by 5. And that creates natural log 6x equals 8/5. now that I've got the natural log cleaned up, I've removed this 5 that was being multiplied. There's nothing in front of natural log. I'm now ready to convert this to exponential form. But you just have to remember, I see people do this all the time, they'll do 10 raised to a power. You just have to keep in mind that if it's a natural log, e is always the base. So give me this column in exponential form, base e. E will be raised to what power? Well, what are logarithms? They are. So the logarithm is good. E to the 8/5 power equals 6x. So once again, let's turn it over to your calculator to do the work. Now you're going to use your e to the x button. And the exponent that it's waiting for, in parentheses, will be 8/5. And you can just hit enter. And again, don't have to write that down. Just let it sit there. And Kate, after we've got e to the 8/5 power, how will we solve for x? Exactly. So just hit divided by 6. And Casey, what is that? Okay, who got it? Oh. Okay. 0.8255? That sounds familiar. 0.8255. Yeah, I remember that one. Any questions? Who else got that? Nice. Oh, okay. Okay. One more. What's my first move? What does my first move need to be in this problem? Let's see if Abby can help us with that. Good call. Divide by -4. That takes care of this number being multiplied in front of the natural log. And I'm just going to use this, leave this as a reduced improper fraction, 13/2. And now we convert it. So show me on your paper how this becomes an exponential equation. So Hunter, what would that look like, exponential equation form? Okay. All right. Turn it over to your calculator. Find your e to the x button. And you can either put 6.5 or 13 divided by 2 in the parentheses for the exponent. Leave it sitting there after you hit enter and divide by 2. And let's see, Heather, when you get that, tell us what you got. Very good. I do remember that one. Good job. Any questions? Pretty good? Nice. Okay, let's do inequalities. Very similar to what we did yesterday. All right, so I noticed that there is nothing in front of the natural log, no operations happening, so I'm good to go. I'm ready to turn this into an exponential inequality, base e. Okay, so it will be e raised to the 6th power, and just keep this in mind when you turn these around. Notice how the inequality, you can think of it this way if it helps. The inequality is pointing at 6. So when I write this in exponential form, it still needs to be pointing at 6. So that's going to mean I need to turn this around, make it face less than. Okay, everybody with me so far? All right, now calculator time. Let's do e to the 6th. Find out what that is. And I'm just going to kind of guide you through some calculator steps here. You've done e to the 6th, and you're looking at that decimal in your calculator. And now we need to do the cube root of that. So the easy way, with that number already there, is just hit this button. And in parentheses, please make sure you use parentheses when exponents are fractions. Raise that number to the 1/3 power. That's the same as the cube root. You can hit enter there. Okay, still don't need to write anything down. We're down to this. Okay, let me just take off what we've already done. We've done that power of 3, we've undone that. And so really, we just have 2 operations left to undo. We just have to make sure we undo them in the right order. We need to add 3 to that number in our calculator. And then we'll divide that number by 2. Because our goal is to obviously solve for x. Okay, so what do we got? $5.1945. Sound familiar? Who got it? Good. And you could say that that number is less than x, or if you prefer, like I do, I like to put my variable on the left. You could say x is greater than that number. Okay, everybody with me? Question? To have you watch the word problem at the end. Let's solve this inequality. It's exponential, base e, so it needs to be converted into a natural log. Okay, so again, just pay close attention. X at this point in the original is, the inequality is pointing at 37.2. So when I turn this around and I say natural log 37.2, then the inequality still needs to be pointing at it. So this one will be pretty easy. We just grab our calculator, hit the natural log button, put in 37.2, and Abby, can you read that off for us? And you could say that number is less than or equal to x, or x is greater than or equal to that number. Either way. Okay. Questions? You feel good about it? Okay, I got about 2 minutes. We learned a formula that you practiced on the last quiz that will help us determine how much an account or a money amount, an investment, grows over time with compound interest. Well, there's a separate formula to handle cases like this where interest is compounded what is known as continuously. And when I get through this problem, you're going to be using this particular formula in, well, several different ways. Here's the formula. If you see the words interest is compounded continuously, it's a completely different formula than what you learned for monthly, quarterly, that big formula. Okay, so the amount, the ending amount, is equal to the amount that we invest, that's the principal, times e to the RT power, r times t power. So once again, p is how much we invested, r is the interest rate as a decimal, and t is the number of years. That's just like we learned previously in the old formula. Okay, and I'm going to walk you through this. Problem number 51 really has 4 parts, so it's really like 4 separate problems. What I'm going to do is very similar to your number 51, so I'm going to need for you to watch carefully as I go through this using this formula. Okay, now we know the formula that is used to handle interest that is compounded continuously on an investment. Let's go through each of these 4 parts of this problem. The first part says, what is the balance of the account after 10 years? You can think of the balance after interest has been applied as the A number. So we're trying to find out what A is in this formula, and P is the amount that we invested. So 3,000 times E raised to this power. So be careful here. When you input the rate, we've talked about this when we did our compound interest formula, when it was like monthly. R is the interest rate as a decimal, so it would be 0.04. And then this means multiplied, so I'm going to put a little mark here that means times. That's not another decimal. This is 0.04 times T is the number of years. Okay, so now we just turn it over to our calculator and you just literally input 3,000. Then do your e to the x button, and it has left parentheses ready for you to input this exponent. Okay, so in that exponent you're going to do 0.04 times, so it literally looks like this, and then 10. And then don't forget to close your parentheses. All right, and hit enter. And the amount that you should show on your calculator, and we always round these interest problems to the nearest penny, is 4,475 and 47 cents. Okay, that's how much an original investment of 3,000 grew to become after 10 years of continuously compounded interest at 4%. Okay, now let's take a look at letter B. How long would it take to double your money? So as we walk through each of these four parts, it's like we're going to be solving for a different one of these variables or letters in our formula. Okay, well if we invested 3,000, doubling that would be 6,000. So we already know the goal, or the A amount, what we're shooting for, is $6,000 from an original investment of $3,000. So A means how much we ended with, P is how much we invested to begin with. All right, and we're still using E, but this time the question is how long. That means how many years. That means we're solving for T. We know what the rate is. It's still 4%. So my exponent for E is going to be 0.04, and then I'm going to do T, because that is basically what we're solving for, how many years. Okay, well just like before, when we had these equations that were exponential base E, we said we always have to isolate E first, and that's still true. So to isolate E, I'm going to divide both sides of this equation by 3,000. And I get 2 is equal to E to the 0.04 T power. Okay, well now that E is isolated, just like we saw in the previous problems, once we get E to the power isolated, we can now convert this over into a natural log equation. So as a natural log equation, it'll say natural log 2 is equal to the exponent 0.04 T. All right, so let's grab our calculator and hit the natural log button, put in 2. And that is 0.693147181. I'm not going to bother writing that down, but I just want to make sure you were able to get that. And now I'm going to solve for T by taking that number that's right now in my calculator, 0.693, on and on and on. I'm going to divide that by 0.04. And the final result, I get 17.3286, but it wants to know how many years, and I'm going to round this off, and I'm going to say approximately 17.3 years. T is rounded 17.3. So let's say it is about 17.3 years. Okay, so now we're ready to move on to part C. And part C says if you want to double your money in 12 years, what rate would you need? Well, once again, I'll just show you the formula. And this time, we're going to plug everything in except for R. And we're going to solve for R. So it's very similar to what we did in part B. As a matter of fact, I'll just go ahead and set it up. Doubling your money, once again, A is 6,000, P is 3,000. We know that T is 12, so we'll just make this exponent 12R. We're solving for the rate. We're still going to get 2 because we're trying to isolate E. Okay, and we can still, you probably don't have that written down. You're going to do natural log 2 again, because this this exponential equation, needs to be converted into a natural log equation. Okay, so this time we're going to do natural log 2 equals, and there's that decimal again. And then to solve for r, of course, we're going to have to divide that by 12. So natural log 2 is sitting in your calculator right now. And if you'll divide that decimal by 12, we will get our answer. And we'll just round this to the nearest tenth. The rate that's needed to double our investment in 12 years, rounded, we'll say 5.8%, about. Now your calculator is showing the decimal 0.0577, but remember to change that to percent form, you move the decimal 2 places to the right, and then you can just round to the nearest tenth. Okay, so my last part, we're still using this formula. If you want to open an account that pays 4.5% continuously compounded interest, and you want to end up with $5,000 in the account after 8 years, how much do you need to deposit? Well, this time, we don't know what P is. So we know that A needs to become, we want to end up with $5,000. We're after, what is it going to take initially to invest over this period of time at this interest rate to get $5,000? Okay, so once again, the rate is 4.5%, so as a decimal, that's 0.045. And this is times, don't think that's a decimal. And it's 8 years, so T is 8. All right, so we can go ahead in our calculator and get this decimal. Let's go to your e to the x button. And we're going to put in 0.045 times 8 and close your parentheses, enter. All right, long decimal. I'll just go ahead and show it. 1.433329415, and don't forget we're multiplying that by P. Okay, so it's probably pretty obvious now how we're going to get P solved for. We're going to do 5,000 divided by this long decimal. 5,000, and I would just go ahead and put all of that in, and then we'll round in the end if necessary. 1.4333299415, and that's 3,488, and this is an amount of money invested, so we'll round it to the nearest penny. We need to initially invest $3,488.38 in order to get $5,000 at the end of 8 years at that given interest rate compounded continuously. Okay, so I just gave you a problem that matches pretty closely to your number 51, so I hope that by having this in your notes you'll be able to do this problem successfully. Work hard on it, and if you have any questions, let me know.